this is Jim Plank, and I'm making a pretty much quick and dirty video here on the Bayesian Optimization Utility within our software framework. This is going to be a sketchy video, but the Bayesian Utility has some components and some quirks, so it's good to go over them so that you don't spend time trying to figure it all out on your own. Okay, so where we are is we are in the framework. Master branch, and as usual, the reference material is going to be in the markdown directory, and in particular we have the utils Bayes markdown file. Now, the whole point behind the Bayesian optimizer is that you are confronted with a ton of hyperparameter settings when you're doing optimization, and often this is choosing your spike encoder, choosing your spike decoder. There might be some application and processor parameters you want to check. There might be eons parameters that you want to modify. And Bayesian optimization is a mathematical technique that attempts to have you optimize this without having to make a ton of calls, so that it is much more effective than, for example, a grid search or a random Monte Carlo search. Okay. Now the utility itself, this is a good picture that ChaoHui drew. So the utility itself is broken up into two programs. There's this C++ program Bayes.cpp, and then there is a Python program, the scikit-opt-py. Now the reason is that the Bayesian optimization utility is written in Python using this GP minimize routine from scikit-optimize, but running it, we wrote the driver program in C++, and the two talk to each other through pipes. So basically, Bayes.cpp sets up the Python program and then talks to the Python program, basically saying, hey, give me another set of hyperparameters. And then the Python program gives it back, and then the Bayes.cpp goes ahead and runs in multiple eons runs with those parameters, determines a fitness, sends it back to the Python program, and then the Python program uses that to generate the next set, etc., etc. Okay, so when you're running this, you should have the framework downloaded, and you should initialize the Python portion of it. You might have to install scikit-optimize. I apologize for installation on Python is always kind of a pain. Here in the main framework, you'll want to go into the main framework directory and do a make utils. And then that will take a little while because it's going to compile about 7 or 8 utils. We'll wait, it won't take that long. They're mostly command line tools for testing different parts of the framework. But the last one here will be a Bayesian optimizer. There it is. Okay, so in the main framework directory /bin/Bayes is that C++ routine that's going to talk to the scikit-optimize one. And if we look at the scripts directory, you'll see there should be, in the main framework, there should be a scikit-optimize. Maybe not. Oh, it's in utilities. Okay, it's in utils. So in the utils directory, there is this Python program that these two talk to each other. Now, I'm going to show you running this from the C++ portion of the framework. It does work with the Python programs, but you might need to do a little tweaking for that. So I'm going to do this with respect to the C++ workflow, because that's, of course, the one that I'm most familiar with. So you go to CPP apps, and the application we'll test here will be the AYSO application. So here we'll say make app equals AYSO app, and then proc equals ravens. And I've already got it done. I've already had it precompiled, so that went nice and fast. Okay, so this is the application we're working on. The AYSO application is this very simple control application where you have an agent following a soccer ball. It runs very quickly, it optimizes well, so it doesn't really need Bayesian optimization, but it's just a good example to show how to use it. Okay, so what we're going to do is I'm going to follow along with the markdown file. Okay, so the markdown file kind of tells you how all of these things fit together, and then it gives you way too much information, which I was said skip when learning, so that you don't spend your time reading parameters when you don't really understand what they do. Okay, but here I've got some examples that you can do. So the first one, what I do is I have a little Bayes run here that you can just copy paste into your shell. So let's do it. It takes about a minute to run. So while it's running, I'll talk about it. So copy paste, excellent, it's working. So now what it shows in the beginning is these are the parameters that it is looking at. So what we're doing here is we're saying we're going to use a spike encoder and we're going to use bins. However, we want our Bayesian optimizer to optimize between 1 and 4 bins and then between 2 and 8 spikes per bin. So you'll note that's 32 sets of parameters. And instead of doing a grid search, we're going to use Bayesian optimization for it. Just a couple things. Here is the training command. You'll note this training command is flawed in 2 important ways. One, I'm only training for 2 epochs, and that's just because I wanted it to be fast. And then 2, I'm only training for 1 episode, which is really bad because it'll overfit to just 1 set of starting conditions. But we'll loosen that up. I just wanted it to be fast. So with this, you can set the iterations per test. So what happens is the Bayesian optimization module starts by choosing 10 random sets of parameters, and then each one of those gets sent to the C++ program, and then the C++ program runs 3 eons runs with those parameters, and then it chooses the median as the fitness to send back to the Bayesian optimizer. After those 10 tests have been done, then the Bayesian optimizer starts trying to generate parameters that it thinks is actually going to do well. Okay, you need to specify the directory. That's where the networks are going to go. So when the optimization is done, in this will run for 20 iterations by default. So there'll be 60 networks sitting here in the networks directory, 1 for each iteration. So then it gives you a little help in case you want to. I'm not going to tell you how to debug. Okay, and now it starts running iterations. So these are all randomly chosen by the Bayesian optimizer. Okay, and you'll note the selected fitness is 0.833, but the best fitness is 0.919. The reason for that is that we ran it 3 times, and the median was 0.833, so that's what we sent to the Bayesian optimizer for this set of parameters. And then but the best fitness overall is being maintained, and that's 0.919. Okay, so this runs. Once we get to iteration 10, it's starting to generate parameters as part of the optimization. And then you will notice that there are going to be times where it will send a set of parameters that you have already evaluated. When that happens, the C++ program maintains a cache of previous runs so that you're not wasting time running the same set of parameters over again. So that when you see hit cache, that's what that means. And I'll talk a little bit more about why this ends up happening more than you think it should. With here, there are just not that many parameters. Okay. When you're done, it'll spit out the 10 best networks, just where they are, what their fitness is, what the training run parameters were. So if we look at networks, right, we'll see there are all the networks named according to their iteration number, and then, well, the Bayesian iteration, and then the eons iterations. Okay, so that's how it works, and so you can use these results however you want. What I do in the markdown is I show an example of me using these to try to actually get some interesting results from the optimization. This test was basically just one so you could see how it works, so you can see it working, but you don't really want to care about the results because the epochs are too low and the episodes are low. Okay, so, and I talk about all that here. So now I do a second test, okay? And this test takes a lot longer, so we won't do this test. Okay, so a couple things. First, I'm doing 5 episodes instead of 1 episode, and that means each optimization is going to be the average of 5 runs with different starting seeds. You need to do this so that it doesn't overfit, especially with control applications. Typically, I like to do 10, but for this Bayesian run, I think 5 is a better value because you're avoiding the overfitting, but in all of these Bayesian tests, we're just using them to figure out what the best parameters are so that then we can set a big eons run on it. And then for that, I'll bump up the episodes to 10 so that we're really avoiding overfitting. Okay, and now what we're doing in this test is we are switching the binning style with bins and flip-flop and triangle. Okay, the number of bins go from 1 to 6, and then the maximum number of spikes is going to go from 4 to 16 with a stride of 2, so even numbers. And this is my starting test, and the reason why is because I want to determine from this test what the best value of max spikes is. And then I'm going to use that value to do another bigger Bayesian optimization, but I'll tell you why I break it up into these two pieces then. Okay, so instead of 20 calls, we're going to do 50 calls. We're going to do 5 iterations per test instead of 3, but otherwise everything's the same. Okay, so when I ran this, it took about 25 minutes on my Mac. And it makes use of the 4 cores. If I remember, I'll tell you about threading in this because it's a little quirky. Okay, but it gave me the following top 10 networks, and I'm not sure what we can get from that. I show you how I generate this Tukey plot from the data since I have the networks. So what I did, since I had the networks, I just reran the program, but instead of training, I tested, grabbed the fitness, and then turned that into Tukey plots. It's a pretty worthless Tukey plot, to be honest with you. I mean, it basically shows me that they're all about the same. But I decided from this, clearly 6 isn't looking very good, and I think 12 is looking too good. And so from this test, I decided to choose a max spikes value of 8. Why? Well, the median's high. Higher than these higher values, and 8 just seems more robust than 4. That doesn't sound very scientific, but there it is. Okay. Then what I did was I set up a much bigger Bayesian run, and I have that here in a file in the scripts directory. And let's just go over it. Okay, so same thing. I'm running the program. I'm training. I'm using 5 episodes. And now I'm switching the encoder, which was previously just a spike encoder, to just spikes encoder to spikes, val, and temporal. Now, the reason I split this up into 2 tests is that the max spikes value isn't used by the val or temporal encoding. And so if I varied max spikes from 4 to 16 like I did in the previous test, and I varied these, the optimizer is going to be generating a ton of hyperparameter tests that end up being redundant, get thrown out, because it'll say, hey, why don't you try val with max spikes of 6, and why don't you try val with max spikes of 10, because it doesn't know. It just sees parameters that it's trying to optimize. So by splitting up the test into 2 pieces, I was able to avoid this because now I'm just setting max spikes to 8 rather than varying it. But so I'm varying the encoder technique. In the interbin or the binning style, I'm varying between these 5 techniques. I'm doing the number of bins going from 1 to 4, and then I'm holding max spikes equal. And then I'm also, in this test, Ravens lets you set an STDP table. So here what I'm doing is I've got 1, 2, 3, 4, 5 different STDP tables that I'm going to test. And then finally, I'm also varying the decoder between a rate based and a temporal decoder, and then whether it uses bins or not. Okay, bump up the number of calls to 100. So this one's going to take a while. And then here, I say just print out the 500 best networks. So 100 runs, 5 per run. This is going to print out all the networks. So I let this one rip. It took 18 hours on my crappy little laptop. And then when it was done, I actually just took the 500 networks, copied and pasted them into a file, had a little shell script. And this is actually a pretty interesting graph, because what it shows is that this STDP table performs pretty badly, and this one performs very well. So that's a nice result. Does show that spikes is performing better than the val or the temporal. Um, Rate and temporal decoding perform about the same, but using bins is an enormous win over not using bins. So big, nice, significant result. And as we've seen in a lot of our control apps, this flip-flop encoder does a real nice job, especially when the domain of your observations goes from like negative x to x. So nice little result. And then what I would do if I were now using this is I would use this to set up just a couple. Well, I would either do Bayesian optimization on the eons parameters like network size and crossover and mutation rate, etc. And then when I was done with that, I'd bump up the episodes to 10 and do a big old eons run that takes a lot of CPU time. Okay, so that's kind of how you can use the Bayesian optimization tool to kind of hone what parameters you select and before you go ahead and do a massive eons run. And I'm going to also state this is not a graph you publish. It's sloppy, but it is a nice graph for just letting you see the results of the Bayesian optimization. Okay, the rest of this documentation, there's a lot of documentation here that ChaoHui wrote. It's all really good. So once you kind of have gotten your feet wet with it, it's good to go ahead and read the documentation before the example and after the example. He spends a lot of time telling you how to identify redundant searches and eliminate them. And also important in here is he has examples of using our cluster where instead of the command, right, here's your command that you're running, instead of that just being a call to your to the app agent code, he has it being a call to srun so that you can run all these on the cluster simultaneously. Now, one quirk of this program, which is okay, it'd be better if we could parameterize it, is that whenever a optimization run is running and you need to do some number of iterations, for example 5 of that optimization, then the program forks off 5 threads running this command simultaneously and then waits for all 5 threads to finish before it figures out what the median is and sends that back to the Bayesian optimization, the Python program. That is quirky, in my opinion. It does facilitate getting some task-based parallelism when you use the cluster. So, right, because that way when you're making srun calls for each one of these, now you've got a different node of the cluster running everything. If you didn't have that, in my opinion, you should only have one thread, do it iteratively, and then use the number of threads parameters in the app agent call to optimize the number of cores on your machine. And my Mac has 4, right? Because in this one, what it does is it actually forks off 5 of these programs simultaneously, and that's not making optimal use, in my opinion, of my 4 cores, because there's going to be a lot of context switching. Okay, I know that was a quick run through. I do wish I had a good example of Python. I don't. I'd be very happy for someone in our research group to do a Python tutorial with Bayesian optimization and to make this markdown page more unified with respect to that. At the moment, this is all I have time for. All right, I hope that's been useful to you. We'll see you in another tutorial.